Okay. Given a 90% confidence interval of 45 and 105 for the mean heart rate, which of the following is the best interpretation of this confidence interval? I believe we are 90% confident that it's between those numbers.
The very first one?
Oh, it's the very first one. Is that what you're saying?
No. Sorry. The first one on the review, which they're supposed to be the same questions. So no, not the first one.
Oh.
All right, so now I better pay closer attention. We are 90% confident that the true mean, yeah, so the second one.
Okay.
Mm-hmm.
Yep. Okay, use the following information. Researchers at the University of Mississippi wanted to determine whether the reaction time in seconds to go, no-go stimulus for males differed from that of females. The researchers randomly selected 20 females and 15 males to participate. The no-go stimulus required the students to respond to a particular stimulus and not to respond to the other stimulus. So we have two independent samples, correct? Is that what that? Yes?
Right, because it's not that like they're couples or something.
Okay.
It's just a group.
All right, so question 3. The researchers decided to construct a confidence interval to determine if the difference in the mean is significant. To determine whether the confidence interval would be reliable, they create QQ plots for both random samples and see that they are approximately normal. Are the requirements for constructing a confidence interval satisfied? Why or why not? So the requirements is that there's a simple random sample. That's good. The mean, the sample mean is normally distributed. So that's the QQ plots determine that, right? And then sigma is assumed to be known, but it doesn't say anything about sigma. So does that mean no, or do we just?
Well, but no, right. Because in the no options, there's not an explanation about sigma.
Okay.
So I was thinking,
Yes.
It's going to be yes because of the plots.
Since it's determined to be normal. Okay, I'm good with that. I actually had to go look up the requirements for the confidence interval because I couldn't remember what they were, and then that started throwing me off on that question. So, okay, I'm good with that.
Okay. So question 4 asks us, of the 4 types of confidence intervals listed below, which one is appropriate for for this experiment? Confidence interval for the mean of differences using dependent samples. Confidence interval for mu when, I forget what that's called, mu or O is unknown. Confidence interval for the difference of means using independent samples. Confidence interval for mu when O is known.
Wouldn't that be the independent samples one?
I mean, that would be my guess.
That's what my guess is too.
I'm glad we're guessing because I'm guessing too. Oh, shoot. Okay, I'm good with that because we don't really talk about sigma except the only thing is in the requirements we know it's unknown, but I think it's more of I think the independent samples is more of the important part of this question and what kind of data we're dealing with. So, okay.
Okay, a researcher is interested in estimating the savings account balance of customers at a large bank. She obtains the savings account balance of a random sample of 30 customers. A 95% confidence interval for the mean savings account balance of bank customers is found to be $3,402.08 and $4,142.75. Which of the following would produce a confidence interval with a smaller margin of error than this 95% confidence interval? Let's say, so basically decrease the sample or the n, compute a 99% rather than a 95, none, or increase n.
Doesn't increasing n increase the sample size? No, sorry. Doesn't increasing n lower the...
Yeah.
Or is it that we want to change? Well, changing the percentage, if we go 99%, that gives us actually a broader range, right?
Mm-hmm.
Yeah.
So isn't it increasing n? So obtaining the balance is 90?
That's what I got.
Mm-hmm.
Okay.
Yeah, because the more people that we have, the more we know that it's going to be right, I guess, or closer.
Okay. So question 6. Factory makes propeller drive shafts for ships. The quality assurance engineer at the factory needs to estimate the true mean length of the shafts. She randomly selects 4 drive shafts made at the factory, measures their lengths, and finds their sample mean to be 1,000 millimeters. The lengths are known to follow a normal distribution whose standard deviation is 2 millimeters. Calculate a 95% confidence interval for the true mean length of the shafts. Input your answer for the margin of error, lower bound, and upper bound. Okay. I lost my notes. So we have the sample mean, so X bar is 1,000. And we know the standard deviation is 2. And we're calculating a 95% confidence interval. So 95 is the
1.96. Right.
And so this is where we're going to figure out, is this M, the formula for M? Is that what I'm...
Yeah, that's what I was trying to figure out, because I know this is a X bar plus or minus 1.96 sigma over square root of n.
Right.
That's for the confidence interval, because we're finding 2 numbers, plus and minus. But I can't remember what the one is to find m.
M is equal to the 1.96. It's what we're subtracting from it's the z-score times sigma over n squared. Square root of n. So we're going to have 1,000 minus 1.96 all times sigma's 2, and n is what?
4.
4? Which is 2, so that's all 1. So it's 1,000 minus 1.96?
That's what I
Is that
got.
right?
Yeah. And then margin of error is 1.96.
That just seems too simple, right?
Oh yeah, that's why I was waiting. Then you got the same thing, so I'm like, okay.
Did you follow all that, Micah?
Yeah, we did 1,000 minus 1.6. That's what I
So
got.
that's the lower bound. And then 1001.96 is the upper bound. And so the margin of error is 1.96, right?
Yep.
So 6 is 1.96. 7 is the lower bound, and that's going to be, hello, computer, 998. Let's get 2 nines in there, 0.04. Save. And question 8 is going to be the upper bound, which is 1,000, 1.96. Boom. Right? That's that.
Yeah.
My computer's. What'd you miss? Sorry, it's acting slow on me. Too many things trying to run at the same time. Okay, I'm good. I'm up to 9. Question 9.
Sweet. All right, so I'll read that. To assess the accuracy of a laboratory scale, a standard weight that is known to weigh 1 gram is repeatedly weighed a total of n times, and the mean of the weighings is computed. Suppose the scale readings are normally distributed with unknown mean mu and standard deviation sigma equals 0.01 grams. How large should n be so that a 95% confidence interval for mu has a margin of error of plus or minus 0.0001?
So n is equal to the z-score times sigma divided by m all squared. So 1.96 times sigma, which is 0.01, all divided by 0.0001. And then we're going to square that. Whoa. How did that get? I got like a big, big number. That doesn't seem right. Times 0.01 divided by whoops. Did you get 38,416?
Which equation are we using for this one?
N is equal to,
Mm-hmm.
and then it's Z star times sigma, all divided by M, and then square all that. It's basically taking the formula for M and solving it for N. So then we were taking 1.96 and we multiply that by 0.01.
Yeah, that's what I did.
And then divide by 0.0001. And then square that.
Right, and so you got 38,416. There we
Yes.
go.
Is that what you got?
Yeah, and
Yep, I got that too.
and honestly, it kind of makes sense because it's saying how large, like how many people do we have to do so that our margin of error is 0.0001. Like that's going to be exact. So we're going to have a huge sample size.
Go for a walk.
But this is crazy to see that.
Okay.
I don't know.
I'm good with it. We're good. Ooh.
The mean area mu of the several thousand apartments in a new development is advertised to be 1,250 square feet. A tenant group thinks that the apartments are smaller than advertised. They hire an engineer to measure a random sample of apartments to test their suspicion. The appropriate null and alternative hypotheses for mu are, let's see, equal to and not equal to and more than, equal to or less than, or can't specify.
It's
I think it's
the last
less
one, right?
because they said it. They believe it's smaller
Right.
Yep.
than advertised. Okay.
Yep. So cool.
Okay. In a statistical test of hypothesis, we say we reject the null hypothesis with the level of significance alpha if p is low, reject the null. So is p less than alpha?
Yeah, I think
Yeah.
less, right?
It's the second one.
Yeah.
Great.
Question 12. A group of statistics students want to determine if students in some apartment buildings get better grades than students in other apartment buildings. They collect GPAs from an anonymous random sample of size 15 from each of 4 different apartment buildings. The data for each apartment building are bell-shaped with no outliers, and the sample variances are nearly equal. Can they use an ANOVA hypothesis test to answer their question?
Well, it's more than 2, so we have to use ANOVA, right? Well, what's the requirements for using ANOVA?
Oh, let me see if I wrote those down yesterday. The data are normally distributed in each group, and the variances are equal for each group.
So yeah.
Are nearly equal, so yes, they can.
Sweet. So the third one?
Yep.
Sweet.
Yep.
All right. A medical researcher is working on a new treatment for a certain type of cancer. The average survival time after diagnosis for the standard treatment is 2 years. So the null hypothesis is that average survival time after diagnosis is the same for the new treatment and the standard treatment. In an early trial, she tries the new treatment on 3 subjects who have an average survival time after diagnosis of 4.5 years. Even though the sample is small, the results are statistically significant at the 0.05 significance level. Consequently, she rejects the null hypothesis. In a future study, it's determined that the new treatment does not increase the mean survival time in the population of all patients with this particular type of cancer. The researcher has committed a type 1 error, incorrectly used a 0.05 significance test when she should have computed the p-value, incorrectly used a 0.05 significance level when she should have used a 0.01 significance level, or committed a type 2 error.
So what did she do originally? In her first one, she rejects the null hypothesis. So it's a type 1 error.
Yeah, because type 1 is when you reject the truth, right?
Yep. And that was the thing that she talked about in our notes, is just make sure you have that little table to reference. She said, I still have to look at that table to get the right quadrant of what it is. So,
Okay.
all right, 14. If the level of significance alpha is made very small, thereby making the probability of committing a type 1 error very small, what happens to the probability of committing a type 2 error?
I think they're inversely related. So if you increase the chance of one, you decrease the chance of the other.
Right. So if we reduce for the type 1, we're going to increase for the 2.
Yeah. Yeah.
Okay.
Because if we think about them making a whole, if one were, yeah, I don't know. Whatever makes sense to you, that I got it. Because I can't explain it, but. Okay.
Okay, there we go. And number 15. The nicotine content in cigarettes of a certain brand is normally distributed with mean in milligrams mu and a known standard deviation 7. The brand advertises that the mean nicotine content of its cigarettes is 1.5, but measurements on a random sample of 100 cigarettes of this brand give a sample mean of X bar equals 1.53. Is this evidence that the mean nicotine content is actually higher than advertised? To answer this, test the hypothesis. H, all that equals 1.5, then the other is being greater than 1.5. So at the 0.05 level of significance, you conclude that you should reject HA. There's a 5% chance that the null hypothesis is true. Fail to reject H0, reject H0. Oh boy.
So I believe because they already did it for us, so they conducted a test with 1.53, which is greater than 1.5. Or no, yeah. So we're going to reject the null.
Well, it's not the mean that's greater, is it? It's the probability that's greater, the p-value. So we need to know the p-value to be able to compare it to the alpha, right? Wrong?
Oh. Okay, yeah. Yeah, no, I was oversimplifying it.
No, tell me if I'm wrong, and how do we find the p-value again? Because it has to do with the test statistics. They didn't give us anything for test statistics, right? So.
Do I need a bucket to go to the bathroom?
No, sweetheart. Love you. Am I making it too difficult? Is it simple?
Well, is X bar the equal to the mean? Is that what the previous notes have said?
X bar is the sample mean. So the z-score is x bar minus mu sigma divided by the square root of n. So if we solve for that, then we can get the probability applet and put that in, right?
Yeah.
One 1.53 minus 1.5 divided by 0.05 divided by the square root of 100. So 6 is the p-value, or no, that's the z-score. Is that right? No? Am I making this too hard?
What'd you get again?
I got 6.
What'd you put into the formula? What numbers?
I got 1.53 minus 1.5 divided by 0.05, which is divided by the square root of 100.
Oh, okay. I think that's where it is because I think we're using sigma and not alpha. Because sigma is
Sorry.
0.17.
Yep, we are. I looked at the wrong thing, so it should be 0.17. Let's try this again. $1.76? 47? So 1.
Huh. I'm still getting something different. I just want to make sure I'm getting the formula right. It's z equals x bar
Mu.
minus mu, and that is over sigma?
Sigma divided by the square root of n.
Oh. So sigma's on bottom.
No. Okay, so underneath the denominator is another division problem. So
Right.
above my bar is x bar minus mu, and then below that is sigma
Ah,
divided by the square root of n.
sweet. Okay.
I didn't print up
That's right.
my study sheet, and I should have, so that I was making sure I have all my formulas on there that we're actually using. That would have been wise of me. Because I keep having to look through my notes to find which formula to use, but I should have had that paper ready. Okay, so did you get 1.7647?
Yep.
Yep, I did too.
And then we shade to the right. And I don't know why, right? Do we just shade to the right? Because that's going to affect our probability. Yes, because it's a greater than, it's not equal to. So then the probability is 0.038. Right? And so the p-value is less than alpha.
Okay, yeah. So then we're going to reject.
Yep.
But yeah, I don't think that
Reject.
I don't think that we're overcomplicating it, because that's the whole process. We want to make sure that we're positive before we reject or fail to reject something.
Mm-hmm.
We're going to need that p-value. So yeah.
Okay, cool.
Okay. You would like to look at the mean number of hours worked for wages per week by male students and female students. You'd like a random sample of 100 for each group and test if those means are different. What is the correct statistical procedure? One sample z-test, independent samples t-test, ANOVA, paired sample t-test, one sample t-test.
It's independent samples t-test.
Yeah.
Because there's no relation between the male and the females. Because it's not like couples or something, right? So then it would be independent samples.
Yeah.
And a z-test is only for one sample, correct? T-test is for multiple. And paired or independent, and ANOVA is for like 2+. Correct?
Mm-hmm.
Actually, the ANOVA would be the F test, right?
Yeah.
Yeah.
Okay. 17. An educator is interested in academic achievement by males and females with similar academic support systems. She decides to use brothers and sisters raised in the same home. Furthermore, she decides to use only brother-sister pairs when they are next to each other in sibling order. Should she use a hypothesis test based on independent or dependent sampling? Well, if we pick the sister, then that automatically picks the brother for us.
Yeah.
So they're dependent.
Yeah. So it's going to be dependent.
Will it be the last one?
Yeah. 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 Because the other one.
Has to do with like what the results would be, not necessarily just the sampling people.
Mm-hmm. I think we lost Taylor.
Well, that's not good. I wonder if he can join us again or if he has to add a new call. But it looks like the next one we need a file. We need the dissolved organic carbon.
Oh, okay.
XL.
Let's save that and open it. Okay. Oh, what's this?
Halfway there.
Living on a prayer.
Okay.
And it always takes Excel forever to open up the first time.
My Excel's open and it's still taking forever for the program or the data to come through. Enable editing. It looks like it's just one sample set, so we're going to use the very first sheet in that other thing, right? So I can just copy. Copy. What's that other one called? Quantitative inferences. Taylor sent him a message. His computer died. Oh no.
Oh, so we'll be waiting a minute.
Yeah.
Oh, goodness. All right, that gives me time to open Excel. All the... Wait, which Excel do we need for the... Oh, wait, we need the one that we've been
Quantitative
using.
inference procedures is what it's called.
That's right, yeah, it's the one we've been using. You know, I realized I never replied to you about the group project.
Oh, and I have no idea what we're actually going to have to do. It could be something where we have paired data or whatever. I don't know. I just know we're going to have to do some kind of research.
Yeah,
So,
I can always go to like the crossroads and take a survey. I think the serial idea you had was pretty good. It seems simple enough.
I think if we do a survey monkey type thing too, we can just throw it out there on Facebook and get random samples too, because I've
yeah.
responded to other people's stuff.
Yeah, that's true. Do you know when that's due?
No,
Okay,
I should look
as
and
long as it's
see
snapped.
if we have more instructions on that. I don't know that she gave us any more.
Yeah.
All right.
So,
Do you have time to keep working, or do you need, to wait on him? I don't have anywhere I have to be till
I
like
have
6.
time. If you want to continue on, that's
No, I can
fine with
wait.
me.
I can wait. Just
Yeah, today's my day off work, so it's actually pretty good for me.
okay, cool.
Yeah. Okay, and we're using the one sample t-test?
I think so,
Okay.
because
Seems
there's only
simple.
one set of data, so.
There we go. Control V. There we go. Beautiful.
So it says a 95% confidence interval.
Make sure that's
Is that
still.
what our thing's set at?
Yep, mine's still 95%.
And
Okay, so.
then how do we know the null hypothesis and if it's greater than or less than? I guess maybe we figure that out as we go through questions.
Excuse me. What are the 4 types of confidence intervals listed? Oh, of the four types of confidence intervals listed below, which one is appropriate for this situation?
Well, sigma has to be known to use a confidence interval, doesn't it? That's one of the, I think the definitions or the requirements just for